Audio Jungle. Audio Jungle.
Yes, sir.
Okay. So we have two-dimensional stress system including shear stress on XY plane, right? So now onward, we'll take the object, 2D object we have here. So on this 2D object, we can say the stress is nothing but sigma y here, sigma y, this is sigma x, right? Also we are considering now shear stress on XY. This is the next, we are taking case 3. In case 2, it was only two-dimensional stress system and there was only sigma x and sigma y. Now we are considering the shear stress also on XY plane. So obviously this is the XY plane. Here if you show the stress, so this stress is nothing but tau xy, shear stress on XY plane, and just equal and opposite because this is complementary stress. So this will be tau xy, equal and opposite magnitude, and here just opposite of this will be tau x. So this is the shear stress on XY plane. Shear stress on XY plane. So basically sigma x and sigma y, this is called a normal stress or also called direct stress on x and y direction respectively. Okay. And what is the tau xy? Tau xy is nothing but shear stress on xy plane, right? This you need to remember. Okay. Again, if you cut this bar, 2D bar, if you cut this 2D bar by one inclined plane, so once you cut, obviously this will be the vertical plane here. This will be the vertical plane, see. So between the inclined plane, this is the inclined plane, okay? Inclined plane. And if you check from vertical to this incline, its angle is nothing but theta. Angle is nothing but theta. Different color. Angle is nothing but theta. All right. Now we'll take this separate diagram for this inclined part. So where is the inclined part? This part is nothing but inclined. Once you cut, then this section you will get here. So I will extend this and my new diagram will be something like this. Right. Okay. I can say.
Sir, can you just show the previous slide?
Right. So here we have taken the portion which is already I explained, because we are interested to get the oblique plane. So how to get the oblique plane in a complete bar? You just cut that section. So once you cut, then this is nothing but, you can say this is L, this is nothing but N, and this is nothing but M. So one triangle you will get basically, this is nothing but L, okay, this is nothing but L, M, and this is nothing but N. And here you got this angle is nothing but, as I told you, theta. Here in this direction the stress is nothing but sigma x, sigma y, and I have shown the shear stress also on the xy plane, which is nothing but tau xy is tau xy. And now this is the oblique plane. So perpendicular to this oblique plane we have normal stress that we have to find, and obviously on this oblique plane we have a shear stress also, so that is tau, simple tau only. So remember this tau xy is the, always remember this tau is nothing but shear stress on oblique plane, okay, and tau xy is nothing but shear stress on xy plane. So we have a difference, okay, so that difference you need to remember. Tau and tau xy both are different. Tau xy basically it is the plane. Where is the plane? If you see the complete object, so this is the complete object here, this is the complete object, and this is nothing but x, and this is nothing but y. So this plane is nothing but xy plane, xy plane, okay. So on this xy plane stress is tau xy, and on the oblique plane, which is nothing but, oblique plane is nothing but ln, okay, oblique plane is nothing but ln. So on oblique plane ln we have shear stress, which is nothing but tau. All right, now guys, because this derivation is now going to be very lengthy, if I will take sigma x and sigma y, if you check my previous case, only sigma x and sigma y I had taken and I had derived, so you got sigma n and tau value, right? Again we'll consider sigma x and sigma y, then again that equation will be very lengthy. Why not sigma x and sigma y already we have derived, why not we'll take only tau xy on the plane and will merge with the sigma x and sigma y, right? Simple. So generally sigma x and sigma y we already have calculated, only now we are going to take tau xy and then we'll mix that, okay. So I will take for this, I will take only this tau xy, tau xy, see, this is nothing but, in this direction it is nothing but tau xy, tau xy, this angle is theta, this is L, this is N, and this is what, M, okay, right. Now if you are interested you can show also, but will not calculate for sigma x, sorry, sigma y here, will not calculate sigma x and y, simply we can show here, but calculation will not perform for sigma x and sigma y. Always remember, only we have to check tau xy. Now what we'll try to do, simple, if you remember the diagram, so diagram we have to draw for the, you know, uh, resolving normal to the ln, because we are interested to calculate sigma n here, this is sigma n and this is what, tau. So I'll show all the stress system here. See, sigma x, sigma y here I can show you, this is what sigma y and this is what sigma x, all right. Now and this is what sigma n, this is what sigma n, and this is what, tau. Can extend this one also if you want. So sigma n and tau we have shown you. Similarly we can show the tau xy now. So here this tau xy is in this direction, this is what, tau xy, and in direction of this sorry, this tau xy I have shown here, and this tau xy, which is downside, I have shown here, right? Okay. And if you check, this angle is what? Theta. So this will be theta. So obviously this will also be theta. This will also be theta. This will also be theta. All right. Now, what we will do, just like sigma n for case 2 we had calculated, so we'll write here resolving normal to ln, normal to ln. This is the ln plane. If normal to ln means along, or you can write along sigma n, you have to resolve the forces. These are the stress. Stress is nothing but, force is nothing but stress into area. Last class I had explained you, one dimension into unit thickness you have to take. So what is the, if you resolve it along the sigma n, or you can say normal to the ln plane, so what will be the first stress? It is sigma n. Sigma n, where it is acting, this is the stress into area. What is the area? Ln, and I told you this is what? Unit thickness. If you remember, last class also I had discussed, this is nothing but unit thickness. Unit thickness. So what will be the area? Area will be ln, one dimension into area. This is stress into area, is nothing but force, which is along sigma n, or you can say normal to the ln. So what is normal to the ln? It is sigma n. All right. Now we'll take the different stresses. Okay, because we are talking about the sigma n here, and we are finding the stress along the sigma n. So now if you check this tau xy, so what will be the tau xy value here? See, basically in just value of this tau xy, if you see, this is the tau xy, so obviously this will be what? Tau xy cos theta, right? Tau xy cos theta will be here. In case of the lm, tau xy cos theta. And similarly, if you talk about this, what we'll write, we can shift this tau xy first, you shift at this point. So once you shift here this tau xy, so what will be this angle? This angle will be, because this is theta, so this is 90, so this will be 90 minus theta. And along this direction, if you check, so this angle will be what? This angle will be, I must write tau xy sine 90 minus theta into what is the area? Area is nothing but mn into 1. This is for the, this is stress. Now coming to this tau xy, you just shift this stress at this point. So this will be tau xy, and if you check, this is theta. Okay, this is the theta. So definitely this will be cos component and this will be sine component. So this is nothing but tau xy sine theta into ml into 1. Okay, sigma x and sigma y, I told you we already have calculated. We are talking only tau xy value. So definitely this is nothing but sigma n ln into 1 is equal to tau xy sine 90 minus theta is nothing but cos theta mn into 1 plus tau xy sine theta ml into 1. So ultimately it is nothing but sigma n ln is equal to tau xy cos theta mn and tau xy sine theta into ml. We can write here sigma n is equal to tau xy cos theta mn divided by ln plus tau xy sin theta ml divided by ln sigma n tau xy cos theta. If you check mn by ln in this triangle, mn by ln, what is the mn by ln? Means perpendicular mn by ln, right? Perpendicular by hypotenuse is nothing but sin theta. And what is the next here? That is ml by ln. ml by ln. ml by ln is nothing but ml by ln is nothing but cos theta. You keep this value here, it is nothing but sin theta tau xy sin theta into cos theta. So what is sigma n? It is nothing but 2 times of tau xy sin theta into cos theta, right? Or also you can write 2 sin theta into cos theta is nothing but sin 2 theta. So tau xy sin 2 theta. So you got sigma n tau xy sin 2 theta. This is the normal stress when the shear stress acting on shear plane only you are considering. We are not considering sigma x and sigma y. We have to calculate all together, but sigma n and sigma y already you have calculated separately, so we'll merge with that. Sigma n you have calculated. Similarly, what we have to do, we have to write for the tau also. So how to write tau? See what line you have to write. Like here you have written resolving normal to ln. Now you have to write resolving parallel to ln. So tau will come. Okay. So I will write here resolving parallel to ln, or you can say it is along tau. So what will be the value? Tau into on which plane it is acting? On tau it is acting on ln plane. So it is nothing but tau ln into 1 into 1. Similarly, if you check the component I had resolved there, here I told you if you write the value, so this is the tau xy and this will be theta. So along this direction it is tau xy cos theta. Okay, this tau xy cos theta on this direction. So it is nothing but tau xy cos theta for mn. Sorry, ml, and that will be in negative sign. Okay, so what value you will write here? You will write tau xy for mn. Mn is nothing but this one. So tau xy mn along it will be tau xy mn, tau xy mn, tau xy sin theta mn into 1. And similarly, if you check tau xy for this, so it is nothing but tau xy, it is tau xy basically lm into 1 into cos theta. Okay, cos theta. So finally what we will get? Tau xy sin theta mn minus tau xy cos theta ln. This is nothing but tau to ln. Now if you write this, you can say tau, which is nothing but tau xy sin theta mn divided by ln minus tau xy cos theta lm by ln. So what value you will get? mn by ln, I told you mn by ln. mn by ln is nothing but sine theta.
Yes, yes.
It is nothing but sine theta tau xy. Obviously ln by then ln will be cos theta. So this is nothing but tau xy bracket, you can write sine square theta minus cos square theta. This is what tau. Okay. Now moving ahead, here it is nothing but we can write tau is equal to what we got tau xy bracket sine square theta minus cos square theta. But you know, if you take common tau xy, then here it will be cos square theta minus sine square theta minus tau xy, and this cos square minus sine square theta is nothing but cos 2 theta. Last class we had seen tau. So what is the tau you got? You got minus tau xy cos 2. This is tau. So now both values sigma n and tau you got because of the shear stress tau xy acting on the xy plane. Hence you got sigma n and tau. What sigma n you got? You got tau xy sine 2 theta. What tau you got? You got just now minus tau xy okay. Now what was the case 2? From case 2, what was the sigma n you have calculated? If you remember, sigma n we had calculated, if you remember sigma n, so sigma n value we already have calculated. If you turn the pages, you may get it.
You are telling for this.
Previous cases we had calculated sigma n, right? So if we'll go and check it, what was the sigma n? Sigma n.
Sigma n.
Tell me.
For case 2 was sigma x plus sigma y by 2.
Right.
Plus sigma x minus sigma y by 2 into cos 2.
Right. Cos
2 theta.
So this is the sigma n. But now if you combine with this, so what is the final you will have? It is nothing but sigma n is equal to, check this equation, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Similarly, we had calculated tau also. We have calculated tau also from the case 2. Can you tell me what was the tau from case 2, if you remember?
Yes. Tau was sin 2 theta into sigma x minus sigma y by 2.
Okay, so it was sigma x minus sigma y by 2
sin 2 theta.
Right. Now if you combine this, so what is the value here? Tau is nothing but, you will have a sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2. So ultimately, see, hope you understood. From case 2 we had taken only sigma x and sigma y, right? And case 3 we had taken tau xy only on xy plane, and then we combined. So ultimately, what is the full phase problem you got? Your full phase problem is, suppose this is the 2D bar xy plane, this is what sigma y, this is what sigma x, and here tau xy is acting like this, tau xy is acting like this, this is what tau xy. Now if you see, if you check the oblique plane for this particular case, the oblique plane you will have something like this. This is the oblique plane. Now here theta is nothing but this one. Still this value will be what sigma y, this is what sigma x, this is tau xy, and here this is what oblique plane sigma n and tau. On oblique plane you got sigma n and tau, and if you see the number, it is nothing but lm and ln, lm and ln. So I'm just summarizing the things. So this is nothing but L, M and N. So on oblique plane, I can write here directly on oblique plane. For this complete system on oblique plane Ln, we have calculated sigma n, and that is nothing but, in single shot I will write this, it is sigma x plus by 2 plus sigma x minus sigma y by 2, in bracket it is cos 2 theta plus tau xy sin 2 theta. Now we'll talk about tau here. In single shot it will be sigma x minus sigma y sin 2 theta minus tau xy cos 2. Okay, so you have to keep this in bracket because this is very special formula now onward, and this is nothing but all right, done.